Okay. And the audio's working? I can't remember if I put it. Okay, cool. Dear Heavenly Father, we thank you for this morning, Lord. We just pray for the people in Brussels that you would just watch over them and just guide the people that are Christians to have this be an opportunity for them to reach the lost. And we just pray that you'd help the authorities to find these cowards who did whatever they did, and just to root out the evil that they have let come to their doorstep. Lord, in your name I pray. Amen. I don't know if you guys have seen the news or not, but it's another big day for peaceful Islam. But, I don't know, you guys know who Jack Van Impe is? No. On occasion, I watched Jack Van Impe when I was little. It was like mid-'80s, right? Jack Van Impe was a contemporary of Jerry Falwell Sr. He was here in the 70s even. And he has this weekly TV show where he shouts at pastors which are corrupt and things like that. He's one of the few remaining voices of righteous consternation amongst the pastorate. I mean, he will call out people as being heretics and stuff like that. He has particularly harsh words for various publishers who have changed versions of the Bible to try to be less offensive, let's say, to the Islamic world by not calling Jesus the Son of God. That's very offensive if you're a monotheist, as they are. But he has a lot of family in Brussels. He talks about them all the time. So, I don't know. He's always talking about how they're very, very, you can't really stand up to Islam in Belgium right now. It's very politically incorrect. And even with that moderation, well, I guess the terrorist suspect from Paris was picked up 3 days ago, so they wonder if this attack this morning has something to do with that. I don't know. Excuse me. Oh, yes. Anyway, back to the math. Here we go. So we're in section 12.5. I'll try to be as quick as I can with the proof here, because I know you guys want to ask questions about homework. So, but this is on alternating series. Save the best for last. I'm going to change notation from the book because all right, so he has been using, in sections 12.1, 12.2, 12.3, and 12.4, he has been using A sub k for a generic term in the series. All right? All of a sudden in section 12.5, he doesn't. I don't think that's good. So I reject his notation. I'm going to use a slightly different notation just so I can emphasize connection with earlier sections. I guess the consistency for him would be that his A sub k's are always positive or non-negative. I guess you could say that. Maybe that's probably his internal logic for writing what he does. Let me make sure I've got the right page here. I prepare these notes sometimes, but if I put them out of order, they work against us, not for us. Let's see here. Yeah, I think that's it. All right, so definition. If you have the sum k equals 0 to infinity of minus 1 to the k, b to the k, which is equal to what? So that would be equal to b0 minus b1 plus b2 minus b3 plus, well, you get the idea. Where the b sub k is non-negative for all k, then the series, and so the terms in the series are what? A sub k is equal to minus 1 to the k, right? B sub k is called an alternating series. All right? Now, Oh, excuse me. Still haven't. So I'm still not looking at the right page in my notes, guys. Give me a second here. Says that. That's just a definition, right? But basically, an alternating series is one that goes plus minus, plus minus, plus minus. Now, that's what I'm calling an alternating series just for the, aha, I knew I was missing a page. That's just for convenience, right? I mean, pragmatically speaking, I would also think something that goes minus, plus, minus, plus, minus, plus, minus, plus is alternating. And clearly what we're doing also has application to something where you have like 300 positive terms, and then it goes plus, minus, plus, minus, plus, minus, plus, minus after that point, right? Because you could always split off the totally positive first 300 terms. That's just a number, and then focus on the plus, minus stuff past that point, right? So saying an alternating series has this specific form is mostly a convenience for the things we're saying today. You could easily see how to like extend what we're doing to slightly more general series, right? Okay, so, excuse me. So here's a definition. I think I got this out of order. I mean, it's not bad to say that. Let me give you an example. Let's see here. So how about this? The sum, let's see here, minus 1 to the k, plus 1, let's say, over k equals 1 to infinity. See, I've already not started at 0, but the reason I wanted to do this is so you'd see, what is this? This is essentially, this is like the harmonic series, right? Like the harmonic series, but what does it do? 1, k equals 1 gives me minus 1 squared, which is 1 over 1. Then you get minus a half. What happens when we put k equals 3? Yeah, plus 1/3, minus 1/4, plus 1/5. You see where we're going with this, right? This has a special name. This is the so-called alternating harmonic series. You could also look at like an alternating p equals to 2 series, like this one, right? Like sum k equals 1 to infinity, minus 1 to the k plus 1, 1 over k squared, right? That would be what? That would be like 1 minus a 4th plus a 9th, right? Minus a 16th plus a 25th, and so forth. See here. Or here's another one. You could look at this. Some, let's say, I don't know, j equals 0 to infinity, minus 1 to the j, all right, divided by 2j plus 1 quantity factorial. Yeah. Okay, so this would be, excuse me, what's minus 1 to the 0 power? It's just 1. What is 2 times 0 plus 1? 1. What's 1 factorial? 1, right? So this is 1. What's the next thing? Minus what? 1 over 3 factorial, right? Minus 1/6. What comes next? Plus 1 over 5 factorial. 5 factorial is 120. And then minus 1 over 7 factorial, and so forth. Excuse me. Every last one of these that I just wrote are convergent. Now, how would you prove that at the moment? It would require some kind of really sneaky business on your part to prove any of these are convergent, given your current tools. We need we need to understand the major theorem about when is an alternating series convergent, all right? But before I get into that, I just want to talk about the intuition for these, just a little bit. So I told you before that this is the alternating p equals 2 series. Remember I told you the p equals 2 series worked out to what? We never proved this, but I mentioned it to you. What did I tell you? 1 over k squared, what does that work out to? Remember pi squared over 6, right? I mean, I have shared this fun fact with you before. It has been known to mathematicians for several hundred years. It's still not super easy to prove. How should this compare to that? Should be smaller or bigger? It should be smaller, right? Because you're like adding half of the terms in that series, right? But you're subtracting the other half, like of the subseries, you could say. So it seems to me intuitively that this must be less than pi squared over 6, right? In other words, I'm saying you could, and this isn't direct comparison test. I mean, the basic comparison test, right? I'm suggesting that if you have, so what I'm suggesting is that if you think about it intuitively, you could see that this converges, right? Because it's clearly smaller than the p equals 2 series, right? But you might worry, well, maybe the minus terms escape to infinity, right? Minus infinity, rather. But you see that doesn't happen because you're always subtracting smaller things, right? So it must be that the negative terms don't win. This must be bounded below by 0 because you're always looking at differences which are less than 1, right? That's less than 1. I mean, these are positive, right? If I parentheses things, it's positive, 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 and so forth, right? So there's no way that this could go to like minus infinity if you're just adding together. Regrouping these terms gives me a sum of positive terms, which we know to be positive, right? If it converges. So anyway, my point is but you see that that's kind of really different reasoning than we've used up to this point, right? It's not exactly basic comparison, because basic comparison was for terms that both have positive, right? Both positive terms. This, on the other hand, I can't use that trick for, right? Because if I was going to try to like compare this to p equals 1, well, that's not a good thing to compare to, right? Because p equals 1 is the harmonic series, that blows up, right? So this idea I just shared with you here totally fails here. But I can prove it to you with a picture, this one. Here's a picture. Number line, here's 0, right? Here's 1. And let me just draw for you the nth partial sums here to show you what's happening. So the first partial sum is this, right? Where's the second partial sum? This much, right? This would be S2. Which is what? 1 minus a half is half, right? And then you do what? You add a third, right? The first 3 would give me S3, which is what? 5/6, yeah. And then you do what? You subtract a quarter, right? So that gets you back over here somewhere. And then you add this. And then you subtract that. And then you add this. Then you subtract that. Then you add this. Then you subtract that. And you add and that. And there you go. It converges to that, whatever that is. You're like, that looks to be about 0.692. Yes, thank you. Very good. It's the natural log of 2. Okay. Now, that's by no means obvious that it's the natural log of 2. But in the next couple weeks, we'll learn how to prove that. Okay? Because we'll uncover the connection between this series and the natural log formula. Anybody care to guess what this series is down here? Nobody's going to guess this because, I mean, the answer is that this is sine of 1. I'm giving you guys these fun foreshadowing examples. Since there's such a small crowd in here, I'm sharing with you my deepest, darkest secrets about alternating series. Alternating series are really awesome, though, because the other thing that's really, really cool about alternating series is any one of these examples, if you wanted me to tell you, like, how far is, like, another, well, I'm going to leave these up here. I have more to add to these as we go on here today, okay? So, so anyway, do you guys understand what an alternating series is at least now? And everything I just told you about, except for the blue thing here, I mean, that's kind of intuition. But obviously this claim and that claim are just out there right now. That's just from the clear blue sky. So here's the here's the observation. Right? There are at least, there are series for which I need to be more specific here. I need to use maybe precise here. Excuse me, a sub k, right? Term with a sub k, for which the sum of the absolute value of a sub k converges. And others for which the series of the absolute values diverge. Now, that's not especially, I mean, you'd be like, well, of course, if the original series is divergent, then surely the series formed from taking the absolute value term by term of the, of the terms, that should also diverge, right? I mean, yeah, fine. What makes this more interesting, of course, is if we insert a word. This is the more interesting thing, right? There are convergent. To make this comment interesting, this observation interesting, I really should insert that word right there. There are convergent series for which the absolute value, term by term, of the absolute value series converges, and there are others for which the absolute value series diverge. If this happens, right, if the absolute value series converges, then the sum of a sub k is said to converge absolutely. Or in other words, aka the series a sub k is absolutely convergent. All right. There are other series, right, which even though the series converges, the absolute value of the series diverges. All right? That's a different phenomena. Those kinds of series, if this is the case, then we say that the sum, the original series, is so-called conditionally convergent. Now, both conditionally convergent and absolutely convergent series are convergent. These are just special cases of convergent series, okay? So perhaps the term conditionally convergent is a little bit, it's kind of a dangerous term. It makes you think, oh, sometimes the series doesn't converge, right? That's not what it's saying. Like, the series is either convergent or divergent once you're given the series. It's either one or the other, all right? So guys, given this language, can you now tell me, looking back over here at my first three, I need to number these examples. Let's call this one 1. Let's call this one 2. Let's call this one 3. If you believe me, all right, about my claim that these, in fact, all converge, which ones of these, 1, 2, and 3, are conditionally convergent, and which ones of these are absolutely convergent? See, you say 1 is what? Right, 1 is conditionally convergent. Let me explain why. 1 has a sub k equals to minus 1 to the k, right? Over k. So what's that mean? The absolute value of a sub k is what? It's just equal to 1 over k, right? And we know that the sum k equals 1 to infinity of, absolute value of a sub k. Well, that's the sum 1 over k. K equals 1 to infinity. It's the diverges, right? By p equals 1 series result. Or sometimes you might say, some people will say it's the p equals 1 series test, if you want to call that a test. We call everything else a test. So you guys like tests so much, so we talk about them some more here. Sorry. It may still be too soon for that. It's always too soon in here. There's too many tests. But see what I'm saying? You take the absolute value of the series, you get the harmonic series. That diverges. Yeah.
This might be small, but one has a sub k is equal to -1. Should that be -1 to k plus 1?
Oh, and that's not small. That's a big deal. I want to be precise, so thank you. Not small at all. I really do want to be in concert with what I wrote over here. Yeah, thank you. And again, my apologies. I mean, I don't know. I guess the definition should allow k to start somewhere other than 0, but enough about that. Understand that we allow ourselves this freedom of the starting point, and I don't want to prove everything here for arbitrary starting points because it's just obnoxious. Proved too much in here already. All right, so how about this one? On the other hand, 2 and also 3 are absolutely convergent, right? Since what? Well, I guess I haven't proved that 3 is absolutely convergent just yet, but for 2, what do we have? We have a sub k is equal to, what is it, minus 1 to the k plus 1, thank you, over k squared. So the absolute value of a sub k just is what? 1 over k squared, right? And the sum, k equals 1 to infinity of 1 over k squared, converges by the p equals 2 series result, right? Or test, if you like. Let's see here. So that's point 1. How about the other one? If a sub k is equal to, what was it? Minus 1. Oh, I'm sorry. I should say a sub j, yeah. Minus 1 to the j divided by, okay, so then the absolute value of a sub j is what? It's, so what does absolute value do to these formulas? It's really simple. Makes everything positive or possibly 0, but it's the natural enemy of minus 1 to a sign, right? It just kills plus or minus 1 things. It's like minus 1 to the whatever after it hits the absolute value is just gone, assuming it's appearing multiplicatively. If it appeared if it appeared additively, I'd have to think a lot harder. Okay, so then what is this? How can you prove that? How can you prove that? How about this? If we have the absolute value of a sub j plus 1 divided by the absolute value of a sub j, what do we get? what am I thinking about here? I'm back in 12.4. Remember I told you guys yesterday, if I see factorial, I think ratio test. So this is made to order for the ratio test. And so what I have here is 1 over 2j plus 1 parentheses plus 1 factorial, right? Times, 2j plus 1 factorial. I wrote it in kind of weird way, but there it is. Let me simplify this a little bit. What we have here is 2j plus 1 factorial divided by 2j plus what? Plus 3 factorial, right? And so this 2j plus 3 we can rewrite as what? How about it's 2j plus 3 times 2j plus 2, and then what's left over? 2j plus 1 times 2j times times 3 times 2 times 1. In other words, it's what's left over is 2j plus 1 factorial, right? Now the reason I wrote that is just what? So I can cancel the factorials, right? Why would I do that? I'm trying to show that this thing either goes to something larger than 1 or something smaller than 1 in the hopes that I can see that it converges or diverges by the ratio test, right? This clearly goes to what? To 0, right? So therefore, the sum of absolute value of a sub j converges j equals 0 to infinity by ratio test, right? I don't think so.
If it's less than 1, it converges. If it's greater than 1, it diverges. And if it's equal to 1, it does not. Okay.
Right. So well, it is true. Well, it is true that the ratio can work out to 0. We do have to do it. There is some fine print here. You can only do it for a series with positive terms. So the question is, before I can apply the ratio test, is this a series with positive terms? Well, is this is a positive term, right? And what else? I think that was it. We need positive terms, and then we can study the ratio of terms in the series. If the ratio works out to something less than 1, it's convergent. Greater than 1, it's divergent. If it's equal to 1, we're out of luck. So it converges by ratio test with lambda equals to 0, which is less than 1, yeah. Consequently, the original alternating series over here, which I have told you through through dark arts, dark mathematical arts, that you will soon learn. Oh, wait a minute, no. I should, it's not, we should not, sorry, let's not glorify black magic in here, it's probably not good. Let's see here, where are we? Oh, yes. So then this is in fact a absolutely convergent series because it's the series of absolute values of this converges, okay? So there you go. There are 3 examples. And in fact, let me give you the major theorem we have on alternating series. Here's the major theorem. If b sub k is greater than or equal to 0, oh, wait a minute. Yeah, greater than or equal to 0. And, then the sum, k equals 0 to infinity minus 1 to the k, b sub k, right? In other words, well, I don't have to write it out. This converges if and only if b sub k is decreasing, and b sub k goes to 0. Let me be careful with the language here. Yeah, let me state this a different way. I don't think this is the optimal way to state it. I'm sorry, guys. I think it's clearer if I reword it this way. Theorem. And this is 12.5.3, alternating series test. AKA A.S.T. Okay. So here's the theorem. Let, let's see here, B0, B1, B2, be a decreasing sequence with b sub k greater than 0. It does have to be positive. That's for one thing I had off. All right, that's the preamble. All right, here's the punchline. The series sum k equals 0 to infinity minus 1 to the k b sub k converges if and only if, which I'll draw like this, b sub k goes to 0. So, yeah. Now, when I was in grad school, I got a handout from some other fellow grad student who was teaching Calc 2, and on his handout, he referred to this as the wishful thinking test. All right, let me show you what he means. Now, what you guys will do, despite the fact, maybe not you guys, but other people. At this point in lecture, I have said probably 10 times, maybe 15 times, that the p equals 1 series is the harmonic series which diverges. If there's anything I've said repeatedly over and over again at this point, you might have noticed that has come up a bunch of times. It came up in the proof of the root test. It came up in the proof of the ratio test. It came up when we were studying the integral test, right? It just came up again today. Right? I'm talking about it again right now. Okay, maybe 15 is an exaggeration. But I'm getting to a point here. So the wishful thinking test is this. It's wrong, but the other one, this one. So you got 1 plus a half, plus a third, plus a fourth, plus right? And the wishful thinking test is, well, a sub k is 1 over k, right? That goes to 0. Okay, that converges. I'm done. What's wrong with this? How do you spell tail? Tail, yeah. I have seen this dozens of tests over the years. Very, very popular conceptual mistake. Maybe the most popular conceptual mistake in this part of the material. What's wrong with it? Yeah, well, okay, so first of all, alternating series test does not apply here because this is not an alternating series. Right. And exactly. Now, we never, ever, ever said that if the kth term in the series goes to 0, that implies the series is convergent. How do we judge convergence of a series? Not by the convergence of the kth term, but by the convergence of the nth partial sum. Right? And the nth partial sum actually involves the log, if you calculate it, by the integral test, essentially. That diverges. I mean, this is the quintessential diverging series that's almost converging. This is the harmonic series. This is, in fact, false. The fact that A sub k itself converges, that does not imply that the sum of A sub k converges. Okay, they're different things. Very different things. All right, I've told you guys this. Maybe I'll do an experiment. I won't tell the later section and see if they make the mistake and you guys don't. What do you think? Oh, but they might watch this video, so I can't be sure. I guess I'll just tell them anyway. It is. I'm not sure if by telling you guys this, I've actually made some of you make that mistake. Maybe it's on me now. So I don't know. But you know, the other grad student I knew, he called this the wishful thinking test because basically what this test says is for alternating series, that sloppy thinking is right. Now, you do need that they're positive terms that are decreasing, right? If they were increasing, what could you have? Why do you need decreasing? If you had positive terms which were increasing, what could happen? You could have like this situation, right? Like you could have b sub k going to 2 or something. So then after a while, you'd be looking at plus 2, minus 2, plus 2, minus 2, plus 2, minus 2, plus 2, minus 2. That will not converge. That nth partial sum will oscillate. In fact, that kind of series you can see diverges by the kth term test, which is that if a sub k does not go to 0, it diverges, right? So the alternate case that you have an increasing sequence here, well, that's not going to work for you. Whether it's increasing without bound or whether it's increasing and going to something finite. So we need decreasing sequence of positive terms, and then we have the alternating series test. Now let me show you the proof. I'll try to be brief, if that's possible for me today. I don't know. Grief. So proof. The proof is really kind of ingenious. Not my proof, okay, obviously. Let's see here. So if you look at, let's see here, S, the nth partial sum is what, you know? As usual, sum k equals 0 to n of minus 1 to the k, bk, right? And let's assume that b sub k are positive and b sub k decreasing. And let's, okay, that's the preamble, all right? Now we're supposed to prove that it's if and only if, all right? What does that mean? We have to prove that one implies, we have to prove it goes both ways, right? So if I assume that the series is converging, so assume that the series k equals 0 to infinity of minus 1 to the k, b sub k converges, right? Then what's my a sub k? A sub k is equal to minus 1 to the k, right? Times b sub k that must go to 0 by kth term test, right? If we have a convergent convergent series, then the terms in the series must go to 0. But what do we know about series which go to 0? I mean, sequence which goes to 0. However, we have the absolute value of a sub k also goes to 0, right? Therefore, b sub k goes to 0. Right, we know that if a sequence goes to 0, the absolute value of the sequence likewise goes to 0. But the absolute value of the absolute value of minus 1 to the k, b sub k, is exactly just b sub k, and so b sub k goes to 0. And there you go, we have what we've done. We've now proved the easy half of this theorem, which is this part. Okay? If the alternating series converges, then the b sub k's goes to 0. Like, well, that was not especially surprising. Okay. Now let's prove the wishful thinking part of it, which is that the fact, that these positive terms going to 0 is enough for it to converge. It's amazing. I need room to write. Man, I hate to erase that stuff. All right, so the other direction. Let's suppose that b sub k goes to 0, right? And what we're going to do is we're going to consider two different things. We're going to consider an even partial sum, and we're going to consider an odd partial sum. So think about the even partial sum to start with. So think about S. And so even would be like n equals to 2j, right? S2j would be what? We start out with what? B naught minus B1, right? Plus B2 minus B3 plus dot, 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 dot. Let's see here, plus, well, I guess, yeah, plus B2j minus 2 minus what? B2j plus 1 plus B2j. Do you guys follow that? All I did was just write out from 1 to 2j, and I wrote the last three in terms of 2j minus 1, and 2j minus 2. Now we're assuming what about this b sub j? We're assuming these are decreasing, right? So if I draw some parentheses in here, you guys tell me what you can tell me. What can you tell me about, for example, this first term here? If it's decreasing, is b1 larger or smaller than b naught? Smaller, right? So b naught minus b1 is what? Positive, right? And how about this? Positive, right? And how about this? Right? So you have all these positive things added together, and then what's this last thing? Also positive, right? But in fact, what you have then is, of course, S2j minus 1 plus B2j, for what it's worth, right? That's sitting there as well. that's not, what I just wrote is totally unsurprising. That's just the definition of finite sum, essentially. That to get to 2j, you go all the way to 2j minus 1, and then you add the 2j term, right? But anyway, my point to you is it's clear that this is positive, right? It's really, guys, just like the picture we drew for the alternating harmonic series, right? It starts out at, the first thing that we hit was the B naught. In this case, B naught is 1. The 1/2 actually is equal to what? That's the B1 in this thing. Well, the significance of it's not that it's B1. The significance of this, of course, is that it's B naught minus B1, right? point is b naught minus b1 is the smallest this thing ever gets. Because you're always subtracting small. I mean, if you just look, I mean, you can see that that's the smallest it ever gets from the picture, but that's in fact how this works, how it's set up. I don't think that comment is necessary for the proof here. I'm just making a comment. Okay, so then what? You got the even partial sum is positive. And what else do we have? Look at this formula. What do we get about the partial sums? What's the relation between 2j minus 1 and 2j? Try to write it out here. Observe S2j, let me just write it again, is equal to S2j minus 1 plus B2j, right? Just make an obvious inequality here. That is greater than S2j minus 1, right? So therefore, if we make a new sequence, right? If we let, let's say C sub j equal to S sub 2j. In other words, C is the sequence of even partial sums, right? What can you say about this sequence C sub j? I mean, I guess this. Yeah, we also have that C sub j is greater than C sub j minus 1. And C sub j, well, we also have that what? 0 is less than Cj, right? It's bounded below. What was I trying to get at here? Yeah, well, that's basically it. In other words, we have a decreasing sequence of positive terms, bounded below by 0. Consequently, by the monotonic sequence theorem, C sub j converges to the greatest lower bound, which is 0. So therefore, C sub j goes to 0. But you can make the same argument about the odd partial sums, right? If I let, if I come up with I need another letter. Let, I don't know. I miss eta. We haven't used eta in a while. Eta, let eta sub j equals to S sub 2j minus 1. You can also argue that eta sub j is positive, and eta sub j is decreasing. Therefore, eta sub j goes to 0. Both of these, again, by the bounded monotonic. Let's just say the monotonic sequence. Good grief, bounded monotonic sequence theorem. So, you see why it's called the wishful thinking theorem, right? Because it's like we've been going over these rather complicated ways of describing when it's a series convergent or divergent. All of a sudden, we learn that if it's an alternating series with decreasing positive terms, it suffices for those positive terms to go to 0. That gives us convergence. That is really nice and simple. Oh, but it's better than that. There's a follow-up theorem to this, the alternating series estimation theorem. What's that say? It says that if you look at the absolute value of the series, the whole thing, k equals 0 to infinity, minus 1 to the k, b sub k, and you subtract from that the sum k equals, say, 0 to n, minus 1 to the k, b sub k, all right? So given a convergent alternating series, that's the fine print here, obviously. Well, guess what? What I've just wrote here, it would be the difference between the whole series and just the first up to the nth term, right? I guess technically that's the first n plus 1 terms if you're counting from 0, right? If we were counting from 1, it would actually be the first n terms. This is the error in Sn, right? It's the error in the nth partial sum as it compares to the value of the sum of the series. It's how far we are off from where it actually goes to, the infinite sum. What do you guys think? So if you look at this example, you can already see it here. So if this is like, we're converging to the dotted red line, right? So if you look at S1, how far is it off? Well, it's like this far off, right? That's the error in S1. The error in S2 is that. The error in S3 is like this distance. See what I'm saying, guys? And if you look at it, the error is always smaller than the next term that you're adding or subtracting. So like, what's the next thing that we go, S1, what's next is what? We subtract a half, right? You go 1 minus a half. So the alternating errors estimation theorem says that the error in saying the whole thing sums to 1 is no larger than a half. The error in S2 is no larger than a third. The error in S3, it's no larger than a fourth. So the theorem is just this. Less than or equal to b n plus 1. Not only are they simple to analyze the convergence or divergence of, they're also shockingly simple to analyze how far off you are at any given point. Like, to apply it here, I could tell you that the sine of 1 minus 1 is less than or equal to what? If you believe that theorem, what does it say? It says the sine of 1 minus, so this is just the stupid first term in this alternating series. It must be less than what? 1/6. Or if I take the absolute value of sine 1 minus 1 plus 1/6, that has to be less than 1 over 120. Try it out. You got your calculator, see if it's true. Fortunately, this is before the synchronicity. The calculators, wireless or not, are not evil. We can trust them. It's good.
Is the sine of 1 in radians?
Better be radians, as this is calculus. Let's see here. I know, right? There's always an issue. Let's see here. Well, first the issue is, how do I change to radians? Setup, yes. Sine of 1, 0.8414 minus 1 is, so minus 0.158. So basically this is 0 point, with the absolute value, 0.1585. What's 1/6? Yeah. Ah! So So we'll say 1.667 roughly, right? By means of comparison, as you can see, wow, that's already pretty close. And if you take the next thing, right? So we take sine of 1, subtract 1, add a sixth, we get 0.0081338, I guess. 1 divided by 120. So, in fact, this is a pretty tight bound. It gives you pretty close to the actual error as well in this case. It's really nice, isn't it? So if you want to know how close you are to the sum of an alternating series, go one more step. That's your error. Whatever you would add or subtract next, that's the error in what you already have. Pretty close to it anyway. Well, that's pretty much all I got to tell you about alternating series. I could prove that. The proof is almost already in front of us, this alternating series estimation theorem. Basically, if you just look at the difference between, like, if you look at the difference between S2j and S2j minus 1, what does it give you? It gives you B2j, right? And if you go to B2j plus 1, that is what? Larger or smaller? It's smaller, right? No. Decreasing. Oh, well, that's it. I mean, if I look at this minus that, in other words, if I look at the case, this is n. Well, anyway, there is some argument to make here, but I'm tired of proving things today. I want to work your homework for you. So I'm going to gloss over the proof of that for now, at least. If we have time after your homework questions, I'll come back and say more about it. But the proof, of course, is also in section what? 12.4? No, 12.5. Now, I'm sorry if you're bored right now. I personally, as a student, didn't find this material terribly exciting my first time through. And it never really got better for me because in my calculus 2 calculus 2, it was about this point in the semester. I mean, okay, so Dr. Lang, he covered a little bit more. We did talk about Taylor series for a couple days, all right? Mostly we talked about the convergence of Taylor series, which we'll do soon, all right? And then he was like, well, I'll see you at the final. We had 3 weeks of class left. I was like, what? Oh, okay, cool. So we just didn't have class the last 3 weeks because he'd gotten through to one to get to. But what I would do with those 3 weeks is show you how we can use Taylor series to calculate all kinds of stuff we can't calculate right now. It will clarify limits which aren't clear. It allows you to integrate things that you can't hope to integrate at the moment. Taylor series open up a whole new world. Basically what Taylor series do is allow you to convert arbitrary functions to polynomials. It's just that they're polynomials without end. So you basically get this arbitrary, as accurate as you like, a description of any function. Well, most functions we care about anyway. And it's called the Taylor series, and we can use it to do all kinds of analysis. It's really neat. So for me, that's where this material really shines. And what we're doing right now is we're just kind of paying our dues. We have to do this in order to understand the convergence of Taylor series, to understand where it goes wrong, right? But what we're doing right now is kind of like reading an instruction manual for some interesting toy when we'd probably be happier if we were just playing with it. But I'm behaving and reading the instruction manual because it is tradition. Like, there's no tradition like a good